off saying here, there's only a few equations. Okay, let me just fix that. It's definitely 5 in our information sheet now, equations. And I would definitely say try and teach your students to use these equations to help them explain things, because yeah, like it is for any other topic, you can use the equations. Like that is definitely Faraday's law, and that minus is definitely Lenz's law. So if we teach them to use their information sheet, we've always said we should have a session on how to cheat with your information sheet. Maybe we should do that at some point. But they can get so much from the information sheet if they know how to use it properly. And so because it's actually supposed to be quite simple, it is a little bit abstract, but I also think that the reason why the kids all find this topic hard is this. We walk into the class and we say, guys, it's going to be electrodynamics, and this is a very hard topic. So it's our fault. We do make it sound like something horrible, and the more we make it sound easy, I think the more the kids will be able to deal with it a little bit better. So I walk in and say, I love this section because there's a lot of stuff you can show them. And please, like Cindy said in the beginning, there are simple things for practicals on electrodynamics. We were talking about a lot of stuff at the marking session that we should share with each other, maybe on the listserv. Small little pracs that you can do. Get a motor from Rutland, they're not expensive. Make your own. I worked with a girl that made her own motor in a box. Big thing with, it was incredible. So please make things to make this more less abstract for your students. Kate mentioned that they can state the laws, and this was very clear in last year's paper, that they can state the laws, but they then can't apply it. So they are getting very good at learning these SAGS definitions word for word, and they still leave out words. They still leave out induced. So we saw a lot of that. But then there was the next question. They got the Lenz's law perfectly right, and then they go and they need to apply that law, and it was actually shocking how many people in the country, or how many students, didn't actually get the next question right. So I would definitely encourage us to let them understand this law first before you actually throw it at them. So what I do is, and I know some of you have been teaching this longer than me and definitely better experts than me, I tell them that there's a new current, because I think what they are doing, and this was clear from the way they answer, and my students always, is what they're doing is they think this is the only magnetic field. So when this magnet is approaching, and they understand that, or they don't understand the law, they know the law, and they say the induced current flows as to set up a magnetic field to oppose the change in flux. They're thinking about this rather than the new magnetic field that is created. So what is very simple to do to make this law more understandable, I don't know if I'm allowed to even say that, is if you say to set up, and just in there say new, so that they know there's a new magnetic field that is going to be created because of the current flowing in that coil. And if you call it a new magnetic field, they don't confuse it with the magnet that is now moving, the magnetic field that is interacting with the other magnetic field, and they can hopefully get it right. And then obviously we're using our right-hand law to get the direction, or to get the North Pole and the South Pole there. But just adding that little word there, I found works very well, that they realize it's a new magnetic field that is created to oppose the change in magnetic flux. Okay, that was just a very quick, not a question. I just thought I'll mention that because we had so many wrong answers. And then this one. This was a question that people struggled with, so I thought, let me talk about this one, since Kirsty asked me to work through questions. Multiple choice questions is always good because it can be turned into a longer question. I actually used this idea and turned it into a longer question for a prelim. So this question caused students a lot of drama, and I thought let's work through this in a bit of detail. So what I do is actually make them do the dots and crosses. Last year was easy for me because I like the practical things, so it was nice to stand in front and be able to show you the dots and crosses. So I'm going to try my best to do it here as well. So I would actually just do the dots and the crosses so they can see. So most of them, if it's a straight conductor, they know that they need to hold the conductor in their right hand, point in the direction of the current. And if we are looking, sorry, my dots and my crosses went a bit whoopee here. But the dots is then on this side of my straight line conductor, the magnetic field is coming towards me, and on the other side it's going away from me. So doing the dots and the crosses there definitely would help. And then I think most of us are quite familiar with, or we have the technology now to do this on our boards, and show them then how these things are moving, because it's very abstract to just look at a little picture like that, and show them then how it's moving. So if I'm looking at, let's just start, if we're looking at A that is moving towards, then when you talk through the question or when you introduce this topic, you can clearly see as I'm moving my little coil into my magnetic field, there's no lines. So there's zero magnetic flux in that area. And again, go back to the equation, we are looking at the area there. So we need to emphasize that we are looking at this little area here. So we're moving into the magnetic field, and there the dots are increasing. And why did I also try to make this a little bit realistic, make the dots go further away. So as we're moving further away from my straight line conductor, they should realize that the field is getting weaker, and therefore they need to spread their dots out a little bit further apart. Can't just be equally spaced out. So as I'm moving, so if I'm doing A, as I'm moving into my magnetic field, the dots are increasing. And here's where I think we overcomplicate it. Keep the language simple, because I can't just say the dots are increasing, but it is the dots that are increasing. So it's the magnetic field that's coming towards me out of the page. Also, this topic, just while I'm saying out of the page, tell your students that the only thing that they have, that the people that are marking their paper is also going to have, is the page. So if they go up, down, north, south, it becomes quite tricky for us to think, what on earth did this student mean? But if they say to the top of the page, or to the bottom of the page, or left, right of the page, into the page, out of the page, the examiners have been very nice, actually giving them options to say into the page or out of the page. But even if they don't, teach them to know that is what the marker is going to have in front of them. So as I'm moving into this field, sorry, I'm getting distracted, my dots are increasing. And now if they know Lenz's law, they should know that the current that is going to start to flow to form my new magnetic field is going to be flowing in a direction to oppose what I am doing. So I have been increasing these dots. So now I want to counteract that. And to counteract a dot, if we keep it now very, very simple, we are just going to go make some crosses to cancel out those extra dots that we now have. And then if they use their right hand rule, and you can just do it if you want to wake up quickly, and you stick your thumb into the page, then you can see that for that one, the current will be flowing in a clockwise direction. So then they can see that it actually happens like that. So let's just do one more so that you can get an idea. Oops. That's not supposed to happen. My dots are not supposed to move. All right, there's my coil again. And now I'm going to move it out of the field. So now I'm going to move it this way. So now what's happening is that my dots are decreasing. So if I'm moving it from there I've got 6 dots, and you can even make them count it. Be part of the class. Let them shout out as you're moving it, how many dots, and they can shout 6 and 4, 2 and nothing, and then they see that the dots are decreasing. So how can I counteract that using Lenz's law? Then we're going to make some dots, and you can point your thumb out of the page, and in that one we can now see that we have an anti-clockwise current. The C C was the, let's just do C. If you then move it up and down in the field, you can see that it's actually nothing is changing. So up and down in the field on that side, and up and down in the field on that side, or I'm glad she's enjoying the presentation. Moving it up and down in the field, you can see there's no change in magnetic flux, and therefore there would be no current induced in this loop, in this closed loop. Remember, it also has to be closed loop for that to happen. Okay. And then this was another question that's similar. So I don't know, Kirsty suggested that I give you some time to do it and then carry on. But I think I'm just going to go through the explanation so that we don't waste your time. I'm not sure if everyone else can hear that someone is not muted. Thank you. All right, so this one also caused a bit of drama when it was asked. This is quite a while ago, though. But sorry, is someone? No. Okay, I'm just going to carry on. So for this one, same type of thing. It was again a loop, dots and crosses, and we had to explain it. Also, the students need to remember that if we are asking, or the examiners are actually very nice, when they ask a law, the chances are that that law is going to be used in the very next question. I think it's something they are very nice, they're very good about. And so it's the same type of thing, and this is where Kate said that they are getting much better at the sequence in how this is happening, and therefore, but I've got my magic sentence here on the side for us to help our students. I have a few magic sentences for different topics. And this is my one for electrodynamics. If we looking at this scenario here again, so if you look at it, it's very similar. And the multiple choice question in this year's paper, although people found it also hard, it was kind of based on the same principle that has been in the paper now a few times. But for this one, it's again it's moving into the coil, so I'm kind of repeating myself in a way. So it's moving into the field, and as it's moving into the field, you can again see the dots are increasing. So that means we're going to do crosses to cancel those dots. And then that means if you stick your thumb into the page, your right hand rule will again show you that there's a clockwise current there. So as it's moving in, here there was nothing happening. So as it's moving into the field, there's my clockwise current being created, and again to form a new magnetic field. Oops, I did not want to kill my little coil there. There we go. All right, and then as I'm moving out, so here you can see nothing is changing, and this was the part that I think students found challenging. As it's